Well, you know what? All right, any questions?
We don't have a comprehensive final, it's just the next test is the,
Correct.
okay, just double check.
Not explicitly comprehensive.
Right, but you, yeah.
Did you want one? I can check.
No.
Okay.
I think we're good, yeah.
All right, just let you know that I care. I would be glad to make you a more difficult test the next way.
Would it be fair to say this will be the most difficult test we've taken this semester? Or is that just me? I'm feeling that way.
Some students have had issues with the last test before. All right, so what do we pick up on waves then? So we've done harmonic motion of an object moving up and down. Now we're going to get into to waves which actually require another dimension. They're no longer traveling along a line in the sense of just up and down, but we have not only particles moving in, every time I'm saying the sentence, I'm keep thinking of exceptions. We're not dealing with harmonic motion, we're dealing with waves that are now traveling along. You can see a pulse. That marker is becoming sad. So first off, in terms of language, there's two types of mechanical waves. Transverse and longitudinal. Some textbooks and some sites will list a third type of mechanical wave called a surface wave, but we're not really going to deal with those. Not every textbook does, because the surface wave is, well, let's talk about the other two and then we'll mention surface waves. So it's all about the movement of the particles in the wave itself. So for example, I have a slinky right here. And I trust that you can see this well enough against the white background. I'm going to release some coils from the top, and the question is, what do you see when I do that? So,
sorry, a downward movement almost? It almost looked as if there was like something moving down.
okay, and so that is an example of a longitudinal wave, because first off, the coils themselves, there was no coil that moved all the way down, but there was a concentration of coils. There's a section where they were closer together that moved all the way down. So that's an example of a longitudinal wave, because the particles moved in the same direction as the wave or opposite direction of the wave. So longitudinal waves, particles move along the way or opposite. So parallel or anti-parallel. So parallel or anti-parallel. I guess I should put the first part. Particles move parallel or anti-parallel to wave. So pulse in the slinky is an example of it. But sound is a longitudinal wave. And in geology, a P wave. The way that the wave moves is that one particle basically pushes into the next one. So if I consider the ring to be the particle, it pushes down on the one next to it, which pushes on the next one, which pushes on the next one. In the case of sound, as the vibration, or as the air is coming out of my throat into the environment, that the particles hit another particle, which hits another particle, which hits another particle. The particles coming out of my throat are not hitting you in the ear when you hear the sound. Now, eventually it might, but What's hitting you is the repercussion of one thing hitting another, which hits another, which hits another. Transverse waves, the particles move perpendicular to the wave. So particles move perpendicular to the wave. And a very brief demonstration, at least here. There we go. So I'm going to send a pulse down through the wave, or I'm going to send a pulse down through the coil. Not as easy to see at this short distance, but so I'm sending a wave down to the other hand. It's bouncing back and coming back, but the particles themselves are just moving this way. So as this particle comes up, it pulls the next particle with it. When this comes down, when this coil comes down, it pulls it back. And so in a transverse wave, we have particles basically pulling on each other, either up or down. If you've been to a gym and dealt with battle ropes, and you're doing this type of maneuver with the battle ropes, transverse waves. So a surface wave, in the ideal case, if you imagine that a wave on an ocean, that the particle basically, in an ideal case, is moving around in a circle as the wave progresses. And so there's some perpendicular and some longitudinal or parallel motion to it. And so surface wave is just a combination of those. There's no reason that we're going to do, we're not going to do anything with this, but I just bring it up in case you come across it. And the other contrast, I've called these mechanical waves because they do require a medium. They require particles to actually move. And the other type, which is not part of physics 151, are, for example, electromagnetic waves, EM waves. Which is something that gets covered near the end of 152. But they do not require a medium in space. You can have electromagnetic waves that does not require anything in space and actually in order to move. However, since these do, these will not travel in the emptiness of space. Thus, in space, no one can hear you scream. Examples of transverse waves. We have, I'll just write down battle ropes. And stadium wave. Because you get one group of people standing up and then down, and then the next people stand up and down, and so you can see this pulse running all the way around, at some point, all the way around the stadium, but the people, the particles themselves, are just moving up and down. And in geology, the S wave. So if we think about these two types of, let's take the geology waves, since the longitudinal waves require one object to hit into another object, these travel through gas, liquids, and solids. These waves, basically solids. If I wave my hand back and forth, are you feeling a breeze where you are? The fact that as I cause air molecules to move in one direction, are they dragging the next ones with them? Not particularly well. That's because I'm trying to produce a transverse wave here in a gas. So geologists, if you take Earth, and there's an earthquake right here, and you got the seismograph over here, so I got this barrel turning around, I got a needle sitting in it, this is an old-fashioned one, needle in it, sort of, when this shakes, it's going to etch in the ink right here. what you find is that there are two types of waves that are produced at an earthquake. You have the pressure waves, and then you have the shear waves, which are traveling around this way. The pressure waves, P waves, also known as primary waves, get here first because they can go through the core, whereas the secondary waves, or shear waves, will go around the long wave. This is how they figured out that the core of the Earth was not solid.
So they didn't know that until an earthquake, not until they studied earthquakes.
I suspect that there was someone who speculated that it was true, but this was, in my mind, the definitive evidence that, because, nothing solid on there to cause the transverse waves to travel that way. They have to go around the long way. Now, longitudinal waves and transverse waves don't necessarily travel at the same speed, but that concept with a bunch of math, and you get there. Now, if you're talking to a geologist and they tell you otherwise, I believe them.
Okay.
My geology is basically what I've picked up on the streets and what my wife has told me.
Okay. Is she a geologist?
She was a geology major.
Okay.
All right, other questions to hear? All right. Now, if I want to represent these waves, it'd be really convenient to represent them in a similar way. Transverse waves are easy enough to represent as just sort of a physical representation of, that's what it would look like. If I've got a rope here and I swing it up and down, I put a pulse in there and that pulse travels, and this is just a side view. But longitudinal waves, if I'm talking about sound, well, sound, I've got these areas where I've got a bunch of particles really near each other, and then places where there's not as close together, and then really high density area and a low density area. This is not easy to draw on a regular basis. So I need to somehow represent this in a simpler way. These sections right here where they have a bunch of particles together, this is known as compression. And the place where it drops off is known as rarefaction. And I could represent it sort of as a classic graph view, where places where I've got a higher density of particles, a greater pressure, I draw a peak, and then where the density drops off, and therefore the pressure drops off, I've got a low, high, low, high. So I can represent longitudinal waves in a very similar manner to transverse waves. It's just that the meaning is different. Here, this is physically that I have particles that have been displaced this far off of the middle. And here, this, in the case of sound, this would represent high pressure and low pressure. So as I talk about waves, I'm typically going to be drawing them like this or this, but it could be referring to a transverse or a longitudinal wave. All right. Vocabulary, very similar to what we've dealt with. Amplitude, I have some middle, whatever the ambient pressure is in the case of sound. The amplitude is just how far off you are. The louder you are, the greater the amplitude. If I go from some point on the wave to the next point in the same spot on the wave, from peak to peak, trough to trough, this point going up to this point going up, that distance there is the wavelength. So we still have wavelength. Period is the time it takes to create a cycle. So this is time to create a cycle of repetitive motion. Wavelength, Another definition of wavelength is not just how far is it from one place to the next, it is basically how far does the wave travel in a period. Because if I'm doing repetitive motion, the first wave has to be completed before I can start the second one. And so the time it takes for the first one to complete corresponds to, well, it's moved some distance. So this is distance traveled in one period. So let's talk a little bit about the speed of a wave. What's the definition of speed? The math definition of speed.
The distance over time?
Yep. So if I look at just the first wave I produce of multiple waves, the distance traveled is the wavelength and the time is a period. So I have a simple formula here for repetitive motion. Frequency is just 1 over the period. And so this becomes the wavelength times the frequency. Now, unfortunately, in physics, more advanced textbooks don't like using F for frequency. They like to use the letter nu. The nu looks like that. Except in some fonts, it looks like that. So you come across an equation and you're going, wait a second, is that a V or a nu? I look for this equation right here because that will tell me for the font used by that textbook which one's a V and which one's a nu. So that's the V, that's the nu, or that's the nu and that's the V. Now I hope you can see why I don't use nu for frequency. But again, I bring this up just in case you're looking at another site and suddenly it looks like there's 2 V's in this one equation. Just recognize one is a V and one is not. My first year here, I was sitting in my office and one of the nanotech students came in and asked if she could ask me a question. I said, sure. And she said, I don't understand why there are 2 V's in this equation. That was the reason, because one was not a V. Now, I'm not going to go through the derivation today. I've got 3 videos that are posted where I go through the derivation. One is not calculus-based, and the other 2 are calculus-based. When you're talking about things, the wave propagation or pulses propagating through some medium, there's a generic formula besides that one over there. That's for repetitive motion, but this one, there's some force term divided by an inertial term. The force term deals with, as one particle moves, how much influence is it going to exert on the next particle? So in the case of the longitudinal waves, as one moves, how much influence does it have in hitting when it hits the next one? In the case of a transverse wave, as one piece moves up, how much is it pulling on the next one? Inertial term basically is how much mass am I moving. So if I'm moving a lot of mass, that's going to slow the speed down. So if we look specifically on the speed of a wave on a string or something really thin, where the diameter of this long object is incredibly small compared to the length. We can be more specific And the video is sort of where I derive this formula. This is tension. And this is linear density. Guessing there's at least one person in here who's had chemistry before. Density, generally symbolized by the letter rho, at least in physics. What is the formula for density? Just the regular old density.
It's mass divided by volume.
Surface density. So we're not dealing with a volume anymore, we're now dealing with an area. Surface density is mass divided by area. Anyone take a wild guess what linear density would be?
Mass divided by circumference?
A little bit more generic than that.
But it's linear. You said distance.
Apparently my reading is off today, unless Brooke said it and I missed it. So you're in the right dimension, it is a one-dimensional thing.
No, you're good. Question, the M that you use for linear density up here on the like V wave on a string, is that supposed to look like an M or is that supposed to look like a different?
That one right there?
Yeah,
It's a mu.
it's me, okay.
The same letter that I use for coefficient of friction.
Yeah.
Now, there are two symbols that are typically used for linear density. Mu is one of them, and the other one is a lambda. So you might also see the formula written as tension over lambda for linear density.
Which also means is that, yeah, is that way?
Yeah, which is one of the reasons I don't use lambda for linear density here. And also why I did not use capital T for tension, because we're dealing with waves here, and capital T is the period. And there's too much doubling up of letters already. All right, so let's see how well this actually, we can demonstrate this. So, take that. We're gonna head out into the hallway. Right with it, I need a rod over here.